Hi guys, in this video we're going to talk about torque and equilibrium. So first of all, remember the formula for torque. These are the formulas that are given on the AP sheet. The first one says torque is equal to the radius, which is perpendicular to the force. So you use this equation anytime that your force is perpendicular to the radial arm, whatever is pivoting. The other way to say that is the radius times the force times the sine of theta. You just need to be careful with this because sometimes it just depends on your perspective. Sometimes you're looking at the sine of theta. If you drew the diagram differently, you might be looking at the cosine theta. So the main thing is just remember that we are looking for the force which is perpendicular to the radial arm or the radius. A lot of times I use a D instead of an R there, and that D just represents the distance from the pivot point, which again is a radius. Okay, let's take a look at our first problem. A punching bag of 60 newtons is suspended from one end of a light horizontal rod, 4 meters long, the other end of which rests against a vertical wall. The rod is supported at the end, holding the bag by a 5-meter long wire that is attached to the wall. On the diagram, draw a force diagram for the rod. Okay, that phrase force diagram, it's like a free body diagram, but since we have more going on than we would in a free body diagram, we actually call it a force diagram. So for a free body diagram, we just had that one dot and there were arrows coming out of that one dot. Well, in this diagram, there are a lot more forces going on and in different places. And so we just have a different name for it, force diagram. Okay, so before we even get to part B, which is calculating, you will need a calculator for this. So make sure you have that calculator handy. And it's helpful if you're doing the calculations on your own so that you're actually learning as we go. Okay, if we look at the information that's given to us, one thing that we are given is that the horizontal rod is 4 meters long, wire is 5 meters long. So we have a 4-meter long rod and we have a 5-meter long wire. We need to know what that angle is because back to the formula, we need that angle. So take a second right now with your calculator and find out what that angle would be. Okay, so if you take a few minutes to look at the diagram, what I did is I did cosine of theta is 4 over 5. So on your calculator, you do the inverse cosine of 4 over 5, and you should get theta is 37 degrees. Make sure your calculator is in degree mode because we are using degrees on this page. Okay, so this angle is 37 degrees. We can also find this angle if we want that because sometimes, depending on how you look at it, you might use that angle instead. So that angle is going to be 53 degrees. Okay, so we have our angles. Take a few minutes to look at the force diagram that I've drawn here. The bag is 60 newtons. The force of tension, we're going to have to look for that. That's going to be along the wire. And there's also a normal force going on between the wall and the rod, and so that has to be there as well. As we look at that diagram, the first question is asking for the y component of the force of tension of the wire. So in other words, I'm looking for this piece here. I can call this force of tension in the y direction. Well, what is that going to be equivalent to? If you take a look at the free body diagram, what is that going to be equivalent to? Well, that's going to be equivalent to the force of gravity on the bag, or in other words, 60 newtons. And we ought to pay attention to our directions. So if the bag is working downward at 60 newtons, then the force of tension in the y direction must be working upward. And so that's the force of tension in the y direction. The next question asks us for the force of tension. So the force of tension in the y direction is 60 newtons acting upwards. Now we want to find that hypotenuse. And so, again, depending on your perspective, you could use the 53 degrees or you could use the 37 degrees and find the force of tension. So take a minute now to look at that diagram, see how you're going to do that, how you would set that up, and then find the force of tension. Okay, you could use the sine of 37 or you could use the cosine of 53. Either way, you're going to set it up as 60 over the force of tension, and your force of tension should be 100 newtons. And your calculator probably rounded it to 99.6 or 99.7, but actually as it turns out, the way it's set up, that actually is exactly 100 newtons. And the reason goes back to this being a 3, 4, 5 triangle. And so that's where it comes from, because we approximated that 37. Okay, so anyway, tension should be 100 newtons. Okay, we have a force that the wall exerting on the rod, and that on our diagram is labeled as the normal force. If you take a minute to look at it, what would that be equivalent to? Well, that should be equivalent to the force of tension in the x direction. So once again, depending on your perspective, use the 37 degree, use the 53 degree, use whatever you know, and see what you can come up with for the force, the normal force, which is the force of tension in the x direction. Okay, for this one, again, you could have used sine, cosine, tangent, whatever works for you. I went ahead and used tangent just because I felt like I knew information where tangent would help. And anyway, when I figured it out, the normal force comes out to be 80 newtons. So again, regardless of what method, you should have gotten 80 newtons. All right, so one of the main concepts that we're talking about is balance here. Like, how is this going to be balanced? And so if we look at our free body diagram, we know that the force of tension works in this up and to the left direction. The up part is balanced by the 60 newtons on the bag. And if it's going to the left, then it needs something to act towards the right. And so the normal force is going to act to the right. And so the direction would be going to the right. And the reason that is to oppose the force of tension in the x direction. All right, let's look at the next question. Well, actually, let's go back and look at the first question for just a second. Because on this question, it says a punching bag of 60 newtons is suspended from one end of a light horizontal rod. And what they mean when they say a light horizontal rod is they mean that its weight or its force of gravity is 0. Now, of course, that's not practical. There are no rods that have no mass. So this was sort of one of those theoretical physics examples. And the next example we're going to get into, well, what happens if it's an actual rod that actually does have weight to it? So if we come back down to number 2, this time now the rod has a mass. It has a mass of 5 kilograms. And I'm going to take a second on my calculator and I'm going to multiply 5 kilograms by 9.8 meters per second squared. And when I do that, I get 49 newtons. Okay, when we talk about the mass of a rod, you know, when we did free body diagrams, don't draw this, but when we did free body diagrams, we just said, okay, there's this dot and everything goes down. Well, on a rod, it's a long mass. So we don't just have a dot, we have the whole mass. However, when we find or when we draw in our vectors for forces, when we talk about the weight, we want to go to the center of mass. So the center of mass on a rod is going to be the center of the rod. And so this mass of 5 kilograms is going to give me a 49 Newton force. So that force, 49 newtons, is acting downward. The punching bag, once again, has a 60 Newton force, also acting downward. We need to draw in one other force, of course, that is the force of tension in the y direction. I'm sorry, I mean just the force of tension. The force of tension is here. We will break it up into components again. And the thing is, because we've now added this 49 Newton force, which was not there in the first problem, our numbers are not going to be the same. So I know we just found the force of tension in the x direction, y direction, so forth. They're going to be different now because we have an additional force coming into play. And then the other force that we do need to take into account is the normal force from the wall on the rod. And you can't see that, but that says normal force down there. The question number 1 says calculate the y component of force of tension in the wire. Here is the deal. Last semester, we spent a lot of time with sum of forces equal to 0 in the x direction, sum of forces in the y direction are equal to 0. Now we're adding a third part of that, and that is that the sum of the torques also have to equal 0. All 3 of those need to be in equilibrium because otherwise something's going to fall or spring up or whatever. So the only way we can have this sitting at rest is if all of these are in equilibrium. So because of that, we're now going to focus on the torque. At various times on this worksheet, we will deal with the sum of forces in the x and the y direction, but for this particular question, we're going to deal with the sum of the torques. Okay, well, what are the torques that we have going on? Remember, the sum of the torques is, the torque equation is radius times force. So one thing we have is we have the force of the bag times the radius. We also have the force of the rod times the radius. And we also have the force of tension in the y direction times the radius. So when we're talking about torques, because our rod is horizontal, then we must be talking about any forces which are directly vertical. If a force is also horizontal, it's not going to make that rod move in a torque, right? It's not going to torque it. If you're pressing on it exactly, it's not going to make it move with a torque. This force of tension is, but we are really only concerned in this question with the force of tension in the y direction because that's the one that's perpendicular. Okay, the force of the bag we decided was 60 newtons, and it is going downward. So let's go ahead and put a negative in front of it because it is going downward. Now, the r is the radius. That's the distance from the pivot point. We haven't talked much about pivot point. You can pick your pivot point anywhere you want it to be. However, the natural point of pivoting, you can imagine if this moves anywhere, this is going to be the pivot point, right? So I'm going to pick that one because it just makes sense to me. You can really pick it to be anywhere you want it to be, but I'm going to pick it to be there because that's where it's going to pivot from. Okay, how far away is that 60 Newton force away from the pivot point? From up above, we found out that that was a 4-meter rod. So that's going to be 4 meters. All right, then we have this rod itself, which is 49 newtons. How far away from the pivot point is it? Well, we decided it has to be the center of mass, and at the center of the mass must be 2 meters away. And both of those, again, are negative because they're acting downwards. The force of tension in the y direction is what's actually pulling it up, so that's going to be positive, and that is acting all the way out here, which is, again, 4 meters away. And so now, if you take your calculator and do some calculations, see what you come up with for force of tension in the y direction. All right, when you add your like terms, you get 338 negative. You move them to the other side, so now it's a positive 338. Divide by 4, and you get 84.5 newtons. And again, let's think about what direction is that going. That's pulling up. Okay, so once again, now that we have the force of tension in the y direction, and we know our angles are the same as before. This is 37 degrees, and this is 53 degrees. Then now, because we have those, now we can go ahead and use that trig, whichever angle you're looking at, to find the force of tension. Okay, so to calculate the force of tension in the wire, what I did is I did the sine of 37 is 84.5 over the force of tension, which gives me the force of tension being 140.4 newtons. The other force that we're looking at is the force the wall exerts sideways on the rod. And again, that's going to be the horizontal force. So if you think about what that would be equivalent to, and you have a couple of options for how to solve that as well. So take a look at your diagram and see what you can come up with for the force of tension in the x direction. Okay, so you should have found the normal force to be 112.1 newtons. I did the Pythagorean theorem, but again, there's a variety of options you could have used there. The next question, what direction does the wall need to push on the rod to balance the forces in the rod, wire, bag system? And on the problem up above, we said it has to go to the right to oppose the force of tension in the x direction, and that was true. And as we come down here, though, we need to consider all of those things going on. In other words, we need to consider the sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the torques. And each of those has to be equal to 0 in order for it to be in equilibrium. And so, yes, there does need to be a force pushing it to the right, but there is another force as well. Because if we think about the sum of the forces in the y direction, if we look at the force for the bag, the force of the rod, and the force of tension in the y direction, then we would have the force of the bag being negative 60 newtons going down, force of the rod, negative 49 newtons going down, force of tension in the y direction is 84.5 newtons going up. If we add all those together, it does not equal 0. All right, if we add all those together, we actually get 24.5 newtons. It doesn't equal 0. In fact, what we're getting is a negative 24.5 Newton total. In other words, we need an additional 24.5 newtons. This one's going down. We need something to balance that going up. So we need an upward direction of 24.5 newtons. So in other words, our force is not going to be straight to the right in this case. It's going to be up at an angle from here. In other words, something has to be pushing it up as well. And so the question is, well, what would that be? Well, think about how this is structured. And if you were going to engineer and make this item, how would you do it? What would be the connecting point here? Would it be friction? Maybe. Would friction be enough? Would you trust it? I don't think I would. I think I'd put a bolt or something in there. So friction could be part of it. And if you were just kind of, rigging it up temporarily, then maybe there is enough friction there. But if you're wanting to put it there permanently, I think that we'd want to put some bolts in there. And so those bolts are also providing that upward force to be holding up the bag. The direction that the ball needs to push on the rod, it needs to push it to the right, and it also needs to push it up. So this is the direction that is necessary for this to hold up. Okay, let's turn to the other page.